So coffee cup calorimetry is the type of calorimetry that we do for enthalpy measurements. And so this is really straightforward to set up because it doesn't have to be a closed system, right? It's open to the atmosphere, so it's done at constant pressure. So what this reaction setup looks like, and this will also explain why we call it coffee cup calorimetry, is that it is a double layer of styrofoam coffee cups. So I'm going to give you a picture that's kind of like a slice through the middle. So this is one layer of styrofoam. And then we just put a second layer around it. You can probably figure out why, but I will explicitly tell you that this is just for insulation. So double layer styrofoam cup. And so it's going to insulate whatever's happening inside it from the outside, so we can actually assume that it is thermally isolated and that none of the heat that's generated or absorbed came from or went from anywhere else. So then it gets a lid, just a little styrofoam lid. And we'll put a thermometer down through here. So thermometer. And then we'll also put a glass stir rod down in here. Probably wondering to stir what, because we don't have any reaction or solution in here yet, but I promise it's coming. Let's make it a different color. So it's going to stir up. You'll have some water in here, and then in the water solution, you'll have something doing a reaction. So really, the orange and the blue together are going to be your system and the surroundings. So this is the reaction in solution. And the water, or we'll just say the solution, is the surroundings. And the reaction is the system. And we have a thermometer there, so we can measure a temperature change in the solution to figure out what's happening in the reaction. So this is an experiment that's really often done in general chemistry lab. And what you would set up is you would set up your coffee cups, you would put your solution in, you would measure starting temperature, you would put in whatever is going to do your reaction, wait until your temperature stops changing, and then measure your delta T. So you'd measure a final temperature, so you have a delta T, I guess. So you measure delta T, and that value is for the solution, right? So you're measuring how much heat did the solution absorb or give off. Well, you would have everything that you need to calculate a Q value for this, right? You could easily get the mass of that solution. Now, if you knew the volume and the density, you could do it that way, or you could just weigh it on a balance. The specific heat capacity of the solution, I mean, the thing is, it's mostly going to end up being water, or almost completely water, so we tend to approximate it with just the heat capacity for water. And then the delta T is what you measure in the reaction that you're doing. So in the actual experiment, you measure it. And if it's insulated, which it is, because we've put it in coffee cups, the heat absorbed or given off by the solution is exactly equal in magnitude and opposite in sign to the heat of the reaction. And we're at constant pressure. So this heat of reaction is QP, And in the last video, we defined enthalpy, and the heat at constant pressure is the delta H reaction for whatever the mass was that you put in there, right? It's an extensive property, so we would need to scale it to be out of moles. So I have an example for this. So I'm going to give the video a little pause, write this problem out, and then we'll come back and look at it. So 0.158 grams of magnesium is combined with enough HCl to make 100 mils of solution in a coffee cup calorimeter. All of the magnesium reacts and gas bubbles appear. The temp rises from 25.6 to 32.8 degrees Celsius. The solution has a density of 1 gram per mil and a specific heat capacity of 4.184 joules per gram degree C. Find delta H for 1 mole of magnesium. So we don't necessarily need it for solving our problem, but just so that we have a balanced reaction, what we're doing here is magnesium solid is reacting with the hydrochloric acid in solution, and we're getting magnesium chloride, which is soluble, and hydrogen gas, which is why we're seeing bubbles. So this is a redox reaction. I know we're not there at the moment for identifying them, but if you were wondering, it is. So with the information that we have, we know the temperature change for the solution, which is the surroundings in our problem. So if we can find the mass, which we'll need the density to do, and we have the volume, so that's going to be just a conversion, and the heat capacity, which we're given, which you can see matches water, then we can calculate how much heat was absorbed by the solution. So Q for the solution, well, the mass that goes in here, it's 100 mils. Get this underlined in a different color. 100 mils of solution with a density of 1 gram per mil. So my mass is also 100. The specific heat capacity is 4.184 joules per gram degree C. And then my temperature change, the final was 32.8. The initial was 25.6. So Q equals MC delta T is 3 joules, so 3,000 joules for 0.158 grams of magnesium. So this is just how much it would absorb for that mass of magnesium. Now, I guess technically we could do this in any order, but the next thing that I would probably do is I'm looking for delta H reaction. So all of this heat that was absorbed by the solution, well, it's, remember, equal in magnitude to the heat given off by the reaction, but it has an opposite sign. So Q reaction is negative 3,000 joules for this 0.158 grams of magnesium. So that's my delta H reaction because that's my heat at constant pressure. And now I need how many moles of magnesium did I actually use out of that 0.158 grams. So this, thankfully we don't have to calculate a molar mass. We just have to go look it up. 1 mole of magnesium is 24.31 grams. So this is 6.499 times 10 to the minus third moles. So negative 3,000 joules divided by 6.499 times 10 to the minus third moles means that 1 mole of magnesium would give off 4.6 times 10 to the fifth joules of heat.